Okay, we're good.
Yeah, this is very troubling. Good old high tech. Uh, well, okay. Well, at least I have a sound. At least I get the audio warning that something has gone wrong. So we won't miss anything. Okay. All right. Back substitution. Um, okay. Um, and this is meant to solve the equation u times x is equal to y, where u is a given upper triangular matrix and y is a given vector that comes from applying all the row operations to b. Okay. So, so this algorithm goes as follows. So I'm going to use I as my row index. I start with the bottom row and work my way up to the top. And in between here, I'm going to compute one element of the solution x. So at first what I do is I set my unknown that I'm going to compute equal to the right-hand side element, so that corresponding element of the vector y. And then I do the equivalent of taking terms from the left side and moving them to the right side that correspond to unknowns I've previously computed. So that's going to take another loop. So I use j as a column index, and I'll start with I plus 1, I plus 2, up to n. And what I'll do is I'm going to subtract off terms where I'm multiplying an element of a matrix, uij, times an unknown, xj, that I've previously computed. And then the last thing I have to do is divide by the diagonal entry in that row. And that's it. That's the whole algorithm. So what happens the first time through when I is equal to n? I set my last unknown equal to the last right-hand side value. This loop won't run at all the first time because j is going to run from n plus 1 to n, and because the starting value is greater than the final value, it just won't run. So this loop is skipped first time through. And then I divide by the last diagonal entry. Then when I go for the second time, I set equal to right-hand side entry, then this loop will run once to subtract off one term involving xn that I've already computed, and then divide by diagonal entry. So this inner loop here runs more and more times with each iteration. So each unknown is more expensive to compute than the last. The complexity well, gas elimination was n cubed, and we could figure it out from the number of loops that it had. What should the complexity of this one be? N squared, because we only have 2 levels of loops. In fact, the number of operations is roughly n squared. So in fact, the coefficient in front of the n squared really is 1. Loops one right after the other doesn't. Yeah. So it's a number of nesting levels. Assuming each loop could run as many as order n times, that's also important to take into account, and that really is the case here. All right, and we have a roughly equal number of multiplications and subtractions because we have a multiplication here and a subtraction here, and then we have n divisions, but that's less significant. So I'm really only paying attention to the dominant term here, which is n squared. Okay. So, so what this means is, because the substitution part is much cheaper than Gaussian elimination, then okay, actually, how much time do I have? Okay. Suppose you have a situation where you need to solve multiple systems Ax equals b. The matrix stays the same throughout the process, and the right-hand side vector b, however, is changing each time. Then what you want to do is apply Gaussian elimination to A only once. That's the most expensive part. It takes 2/3 n cubed operations. And then you can apply those same row operations to each b, and then also perform back substitution with each right-hand side vector that comes out. So, so you're trying to do Gaussian elimination as few times as possible, then you can repeatedly do a back substitution part. And this part that is really what depends on the right-hand side, and only one step of Gaussian elimination, which can also be done as a separate process. Okay, but really there's 3 stages to the process that should be kept separate. One is row operations only on A to make it upper triangular. That's step 1. Second thing is applying those same row operations to B just to update the other side of the equation. Now, I've lumped those 2 together on the previous board, but again, they should be treated as separate. Then, once both of those are done, we do this back substitution. So really it's a 3-stage process. That first stage you do once. The other 2 stages can be done with any number of right-hand sides, and that's the most economical way to go. Now you might think, when might that happen? Where you're solving this system many times with the same matrix and different right-hand sides. And actually, I have a really good answer for that. Suppose you're solving a system of ordinary differential equations, and you're using an implicit time-stepping method. Then what happens is, generally you have to solve some system of linear equations at each time step. And if your coefficients of your differential equation are not changing over time, your matrix will never change. But your right-hand side will keep changing because it's varying over time as from the solution. So, so in fact, that's what will happen is you'll be in exactly that situation. Same matrix, multiple right-hand sides. So what you would do is Gaussian elimination on the matrix once before you start this time-stepping process at all, and then you'll just keep going with the applying the row operations to your right-hand side and your back substitution every single step. So that really is a practical application of that. Okay. But now what I want to do is describe in a more formal way how we can view this process of solving a system of equations in terms of matrix factorization. Okay. Now, so a row operation that we use in Gaussian elimination, row I is equal to itself minus the multiplier times row way we can actually describe this in terms of matrix multiplication. So we're multiplying A on the left by a matrix of this form. I'll call it capital Mij. So it's a matrix that has ones all the way down the diagonal, zeros above, and then actually most of the entries below are also 0, except in column J, row I, we have a minus Mij, and then everything else is 0. So what's happening here is, because we're multiplying on the left, we're affecting rows, whereas if you're multiplying on the right, you're affecting columns. So all the other rows besides row I are not going to change at all, because in every row except row I, there's only this 1 in position I, so it preserves that row. But in row I, we have this, and then we have a 1 here. So this is, so row I is equal to row I minus Mij times row J. So by multiplying on the left by this matrix, we actually perform that row operation. Now, what type of matrix is this? Yeah, so it's lower triangular because everything above a diagonal is 0. But because all the entries on a diagonal are 1, this is called unit lower triangular. So the definition is Aij equals 0 for I less than j, and Aii equals 1. So this second part is what makes it unit lower triangular. And I've used this notation before for lower triangular, but if it's unit lower triangular, I'm going to put a 1 here, so I have lazy shorthand for that too. And just as these row operations are called elementary row operations, this is called an elementary row matrix. And there are also matrices for the other kinds of row operations, which we won't really need here. Like for interchanging rows, that's a permutation matrix, which are because we're performing interchange, and we'll deal with those later on. Okay. Now, the nice thing is, a unit lower triangular matrix, if you multiply those kind of matrices together, they're still unit lower triangular. If you invert a unit lower triangular matrix, that also is unit lower triangular. And that's something that we'll be able to take advantage of. Now, suppose we accumulate these matrices. We're working on a particular column, column J, and we eliminate all the entries below the diagonal in that column. Then that means effectively we can think of it in terms of multiplying several matrices of this form together. So now if I look at things in a column by column fashion, I can show you what that looks like. Okay, so I'm going to use this notation. I'll let A1 be equal to the original matrix A, and AK plus 1 is a matrix that you obtain by performing Gaussian elimination entries in column K. So in other words, A1, I haven't done anything yet. I eliminate subdiagonal entries in the first column of A1, and I call that A2. Then I work on the second column of A2, that gives me A3, and so on, until I get all the way to AN. That's my final matrix. So what that means is each new A is equal to the previous A times this matrix, which I'll call MK. MK is a product of unit lower triangular matrices, all of the form that I wrote in the previous board, with these multipliers in the same column J. So it turns out the product of these entries is very easy to describe. So we have, it's unit lower triangular. So we have ones on a diagonal, zeros above, and then in column J, I have all my multipliers negated. So M J plus 1J minus M J plus 2J, and I keep going all the way to the bottom, M NJ. So all the multipliers I needed to eliminate entries in column J, their negatives occupy column J. All right. So what happens is, if I start with A, I apply M1 to it to work in the first column, and this is A2, because A itself is equal to A1. Then I apply M2 to that to work on the second column. It gives me A3, and I keep going all the way down to the last column I work on, column n minus 1. And that gives me my final matrix, which in my notation is AN, but that is a upper triangular matrix, U. So A times a whole bunch of unit lower triangular matrices gives me an upper triangular matrix. That's what the Gaussian elimination process is doing from a matrix multiplication point of view. Okay. All right. Also, these same row operations are being applied to right-hand side vector B. So I take my original B and I multiply it by the same matrices, M1, M2, down to Mn minus 1, and that gives me a vector Y, and that vector Y is, and the matrix U, are fed into back substitution. Okay. So we're using these matrices for both purposes. Okay. Now, so now the fact that all these M's are unit lower triangular gives me a simpler way to describe the whole Gaussian elimination and back substitution process. Somebody needs a pen down there? Okay. So properties we're going to need of unit lower triangular matrices is that unit lower triangular times unit lower triangular equals unit lower triangular, and the inverse of a unit lower triangular matrix is also a unit lower triangular matrix. Okay. Now, I'm going to define LK to be the inverse of each mk that I wrote in the previous board. And it turns out that inverse is very easy to describe. It's actually the same matrix, except for one thing, is the multipliers are no longer negated. So it's just the multipliers occupying column J. And then you have ones on the diagonal, zeros above, 0 everywhere else below the diagonal. Okay. Now, so from what I wrote on the previous board, if I take all those m's and move them to the other side, I have A is equal to, so I start multiplying by mn minus 1 inverse and so on. I'm going to get m1 inverse, m2 inverse, whoops, all the way down to mn minus 1 inverse times u. But the inverses of these m's are these l's. So I have L1, L2, down to L n minus 1 times u. So all of these inverses are unit lower triangular. If I multiply them, that's also unit lower triangular. So I'm going to define this product of these unit lower triangular matrices as L. So now what I have is A is equal to L times U. U is the upper triangular matrix we get from Gaussian elimination. L is the unit lower triangular matrix we get that actually performs all the row operations. Now, we know what each of these m's look like. We know what each of these l's look like. That's right here. What about the product of all of them? What does that look like? Fortunately, we have the answer to that too. L is just a unit lower triangular matrix where the lower triangle is filled with all the multipliers that were used throughout the Gaussian elimination process. Okay. So because of the nice structure of each of these individual L's, accumulating them all into this one big product, the multipliers are stacked on top of each other like they're being superimposed in a way. So now we know what L looks like. So you think of it as just a storage space for all the multipliers. In fact, that's how Gaussian elimination is typically done. Your matrix A comes in, you're reducing it to upper triangular form, and then the multipliers that you compute in the process, you can store them in the lower triangle. Because that's no longer needed by A. In A, they're all becoming 0. So you might as well use that space for something, if you can. Okay. So this is called the LU factorization, or LU decomposition of A. Not every matrix has an LU factorization. Like, what if you needed to swap rows to avoid dividing by 0? We'll get to that later, but for most matrices, this LU factorization does exist. Okay, now, and it's just a natural product of Gaussian elimination, that you have a record of what you did, and this is a result of that. U is a result of that process. So now I can describe the whole process of solving AX equals B in terms of the LU factorization. Each. So what you do is, from AX equals B, I can replace A with this LU factorization. So if LUX is equal to B. Now, this vector U times X, I'll group that together, and I'm going to call that Y. So that means that L times Y is equal to B, and U times X is equal to Y. So now I can describe, because now we have all these systems of equations, here's what you actually do. So first you perform Gaussian elimination. And that factors A into this product L times U. The cost is 2/3 n cubed floating point operations. Then those row operations that are recorded in L now need to be applied to B. And that process is called forward substitution in contrast to back substitution. So what you do is you're solving Ly is equal to B. Now, the forward substitution algorithm is in the notes. It's very similar to back substitution. You're just doing everything from a first row on down for lower triangular as opposed to a bottom up for upper triangular. And this costs roughly n squared floating point operations, just like back substitution does. This has the effect of applying all the row operations from Gaussian elimination to B. So if you had this as an augmented matrix, Gaussian elimination would actually accomplish both of these things. And then the last stage is back substitution. And you use that in order to solve the upper triangular system, U times X is equal to Y. So both these systems emerged from here once we plugged in the LU factorization for A, and that takes order n squared floating point operations. So if you have to solve many systems of form AX equals B where A never changes but B does, you do this once, and then these second and third steps can be repeated. Okay. Questions about this three-stage process? So it's what you did in 326. It's just described in terms of matrix factors. And the forward substitution algorithm for a unit lower triangular matrix, you start from a first row and go all the way to the end. And you so you start by setting your unknowns are your y's. You're setting them equal to the right-hand side entry. And then you have a nested loop that goes from columns 1 to I minus 1. So all the columns to the left of the diagonal. You're moving those terms to the other side. For corresponding to unknowns you already computed. And then that's it. So that's the whole algorithm right there. 2 levels of loops, so that's why it takes n squared operations. How come I did not need to put a step down here to divide by a diagonal entry? I needed that in back substitution. How come I don't need it here? It's 1. Yeah, this is a unit lower triangular matrix. The diagonal entries are 1. If I needed forward substitution for a general lower triangular matrix, I would need a division step here. Okay. Well, I'm out of time, and that's far enough anyway for today. So we'll keep talking about Gaussian elimination related issues into next week.
Bye.
What?
Bye.
All right.